Hi everyone, today we're going to be looking at chapter 20, lesson 2 of cosmology. We will first look at Hubble's law. We will model of an expanding universe supported by the red shift, so that's quite an important one. We're going to show Hubble's constant. We're going to talk about the Big Bang theory, the experimental evidence for the Big Bang theory, especially including redshift and microwave background radiation. We will also talk about how Big Bang theory was developed and accepted, that it also gave rise to space-time, the estimation of the age of the universe. We will see how to do that. It's quite nice actually. The evolution of the universe after the Big Bang to present, and the current ideas in terms of dark energy, dark matter, and only very bit of ordinary matter. Okay, so let's start with firstly Hubble's law. Now, before we go into Hubble's law, we'll talk about what brought up Hubble's law. So Hubble, in reality, he analyzed a lot of Doppler shifts from the absorption spectra of different galaxies that were distant from us. So basically, he collected as much as he could, obviously, because he was just at the beginning of the observation that he was making. And he measured basically the Doppler shift using the absorption spectra from many distant galaxies. And he noticed two things. First one was that the light from most galaxies was redshifted. And we know that if it's redshifted, it means they're moving away from us. So the relative velocity was moving away from the Earth. The second point he noticed is that the further away the galaxy was, the greater the redshift, so the faster it was moving away from us. So he decided to plot this on a graph. So he said, okay, I'm going to plot the velocity that is moving away. Recession velocity means it's moving away from us. And the distance that he measured roughly. By the way, distance is quite hard to measure in terms of astronomical distances. So most of the errors that we will see later comes because of this distance. So yeah, he plotted the distance against the velocity. So let's say if we focus on this point, that's the recession velocity of a galaxy at a specific distance away from the Earth, basically. And it's measured in megaparsecs, so it's easier for them to record it. And the recession velocity is in kilometers per second. So you have to be a bit careful with the units depending on what it asks you, because it's one of the parts of the course that you need to be able to do. So it's just kilometers per second in this case for the speed, the velocity, and the distance is in megaparsecs. So what he said from this graph, since you can see that the points are not very close to the line, so you don't really see a very perfect pattern, but you see a general pattern. So you draw the line of best fit, which is the red line that goes through most of the points, in the center of most of the points. So he said, so his law says, it's based on this basically, that the recessional speed of a galaxy is almost directly proportional to its distance from the Earth. So in other words, V is directly proportional to D, with V being the recessional velocity, now, usually if it's plotted on a graph, it's kilometers per second, but if you're doing calculations, you will need to be careful. And this is the distance from the Earth. So you need to know Hubble's law. Is very, very important in terms of what we will see next as well. Another good point to mention here is that even though most of the galaxies show a redshift, some of them still show a blue shift. Those galaxies are actually moving towards us due to the gravitational attraction they have to our galaxy, not because there is a misplaced pattern. Now the redshift is actually showing that the universe is expanding since all of the galaxies are moving away from each other. So this is something that we'll come across again in the central part of the video. So from Hubble's law, we can come up with the equation of his law. So the recession of velocity is equal to the Hubble constant times the distance from the Earth. So we'll be able to calculate the recession velocity of any galaxy if we know its distance from the Earth. Usually Hubble's constant will either be given to us or you will have to get it from the graph. So remember, the graph has the recession of velocity against the distance from the Earth. Depending on what units you're given, you'll have to change them. So be a bit careful with that. So you have the line, you just get the gradient, and the gradient will be equal to Hubble's constant. Other times you might not even need to get the gradient, you might just need, you might be given the Hubble constant, or you will have calculated in the previous part in a question, and so on. So what are the Hubble constant's SI units? Now we know that usually, so I'll rearrange the equation for Hubble's constant to be the subject. So we have speed divided by distance. We usually know that speed is given in meters per second, and that distance is given in meters. So the Hubble constant SI unit will be per second. However, since cosmologists tend to use kilometers per second for speed and megaparsecs for the distance, then we can use a different unit. So in this case, it will be kilometers per second divided by megaparsec. So the unit will be kilometers per second per megaparsec. So both units could be used depending on what the question actually asks you and how many marks it is. You might need to convert, or you might not have to convert between them. Now also, as a rough estimate, because the Hubble constant is not fully quite a fixed number, and like I mentioned before, this has to do with the fact that when we measure distance to galaxies, it's not as precise as we would like it to be. So the value of the Hubble constant tends to vary a lot. With the most accurate one that they've recorded back in 2013, it's about 67.8 plus or minus 0.77 kilometers per second per megaparsec. Now I can change that into the standard units, and to do that you just simply work through the units of what they mean. So this is kilometer per second. I need to change it into meters per second first. And to do that, I just simply multiply the value by 10 to the power of 3. So that's 10 to the power of 3. So it's going to be 67.8 times 10 to the power of 3. And then you will divide it by what 1 megaparsec is. So we already are given what 1 parsec is in meters. So you also need to take into account this megaparsec. So that's going to have divided by 3.1 times 10 to the 16 times 10 to the 6 for the mega. Okay, so once I do that, I get 2.19 times 10 to the minus 18 per second for Hubble's constants in terms of SI units. Okay, so just to wrap this up, Hubble's idea that that most of the galaxies are moving away from us and at the fastest speed means that the galaxy is expanding. However, that's not caused by the fact that the other galaxies are flying away from us. They are actually moving away from us because space itself is expanding. And a good way to visualize this is to think about a balloon. Like if you draw if you get a balloon, before you blow it up, then just draw a few dots on it if you have any balloons at home. Now, if you start blowing air into the balloon, you will notice that these dots, so they will no longer be that close together, but instead they would have moved further away from each other. That's because the space itself between the galaxies is getting bigger. So each galaxy will see all the other galaxies moving away from it, even though they're not at the center of the motion. That's how we see things as well from the Earth. So even though the balloon idea has a bit of a concept, it's got a lot of misconceptions that can be created by it. The fact that we are expanding into nothingness and not on a balloon surface. But yeah, that's one way of imagining exactly why we assume that it's expanding. Not assume, why we know the universe is expanding. Just to quickly check on the learning outcomes, we talked about Hubble's law, with h not being the Hubble constant. We talked about how the redshift is showing that the universe is expanding. And we also looked at how we can calculate the Hubble constant in both kilometers per second per megaparsec and per second as units. So we're going to have a go at the Big Bang Theory and the evidence behind it, and then look a little bit into the evolution of the universe. So for the Big Bang Theory, one of the evidence that led to it was the fact that the universe is expanding. So we've seen that with Hubble's law. So if it's expanding, if we reverse time, it means that if it's expanding and cooling down, then it means that before that, everything was started at a single dense hot point. So that's what Big Bang Theory states, that everything, all matter was contained in a single dense hot point, which marked the beginning of space and time in that big explosion. So before it started expanding, there was nothing before the Big Bang. So for Big Bang Theory to be accepted by the scientific community, it needs to be supported by the evidence. So far, every theory that they have about the beginning of the universe does not have strong evidence as the Big Bang Theory does. So in this case, we're going to look at the key evidence that involves Hubble's law and the microwave background radiation. So Hubble's law states that the galaxies are receding from each other due to space expanding in all directions. And the evidence is the red shift that we see constantly. Microwave background radiation. Now, this is the second piece of evidence that's very, very important. Now, when the universe was very, very young, it was very hot and dense, and it was filled with high energy gamma photons. Now, as the universe started expanding, you can imagine that very high frequency wave stretching with space and time as it expands. So what you will expect is, since it stretches now from gamma, we have an EM wave that has a longer wavelength. So it kept stretching over time, and currently is stretched so much that it reached a wavelength of about 1 millimeter, which is in the microwave range. So now we observe that energy coming from all directions. So if you have a telescope that can be used to collect a microwave radiation, to pick on microwave radiation, it's all over the universe. So the microwave background radiation was actually discovered by accident using a satellite, and they also found that it corresponds. So since over the years the temperature has reduced, they have found that the temperature of the universe now is 2.7 Kelvin. That's really, really low. And if you go back to the previous lesson that we've seen, in the previous chapter that we've seen how a black body, anything can be treated as a black body. so it emits black body radiation. Well, that radiation at this temperature has a peak in intensity. So if I remind you this, the peak in intensity is at 2.7 Kelvin. Sorry, that's 2.7 Kelvin. And the wavelength, so this is the wavelength against intensity for black body radiation, so that would be at 1 millimeter. So the peak wavelength corresponding to 1 millimeter in the microwave region of the spectrum. So these were the key pieces of evidence for the Big Bang theory. So we can also estimate the age of the universe by assuming that the universe expanded uniformly over time since the Big Bang. Even though we know that it's not expanding uniformly, so the reality is that the expansion is accelerating, we will still just assume that it's uniformly expanding over time since the Big Bang. So we can use the equation speed is equal to distance over time to calculate the age of the universe. So the age of the universe will be the speed the distance divided by the speed. But we also know that the recessional speed of galaxies is given by Hubble's law, with v being the recessional speed, Hubble's constant, and the distance from the Earth. So I can replace v with h naught d. So that will be the time is equal to the distance divided by Hubble's constant divided by the distance from the Earth. Distance and distance can cancel out, and we have time is equal to 1 over Hubble's constant. I also mentioned before that Hubble's constant usually has a range of values because of the fact that we have the distance is not measured very well. But if we do use, let's say, the Hubble's constants we calculated already in this video, then we can say, okay, that's 1 over 2.2 times 10 to the minus 18. And this is how we get the age of the universe, which will be equal to about 4.5 times 10 to the 17 seconds. Now, if you divide that by how many days are in a year, and so on, you will find out that this is about 14 billion years. So the universe is nearly 14 billion years old. So we have spoken about the Big Bang theory, that the universe started from a very hot, dense point, and since that space and time started as well. Before that, there was no space and time. We looked at the experimental evidence for the Big Bang theory, including how we have microwave background radiation, and since it expanded, it has cooled down, which peaks at that radiation either way, how that stretched from high energy gamma photons to microwave as well, and the red shift. That's very, very important. Also, you need to talk a little bit about the development and acceptance of the Big Bang theory by the scientific community. So the fact that nothing else matched the microwave background radiation or could explain the microwave background radiation compared to the Big Bang theory, then and the evidence that could support the Big Bang theory are stronger and accepted by the scientific community. Also, the idea that the Big Bang gave rise to the expansion of space and time and the estimation of the age of the universe using 1 over Hubble's constant. And remember, Hubble's constant has an SI unit of per second. So if you do 1 over per second, you take the time in seconds. So we're going to look at the evolution of the universe after the Big Bang and the current ideas used in terms of the universe made up of dark energy, dark matter, and a small percentage of ordinary matter. Okay, so what we have is that since the time of the Big Bang, we have certain timings that show what happened in terms of the universe's age. So time and space were created in the Big Bang. So before it was a very infinitely dense, hot point. Then after 10 to the minus 35 seconds, the universe started expanding very rapidly, and it had a lot of high energy gamma photons. At this point, there's no matter formed yet, because the temperature is so high. It's 10 to the 28 Kelvin at that point in time. So at 10 to the minus 6 seconds, the first fundamental particles start gaining mass through a process that involves Higgs boson. So quarks and leptons start forming at that time. At 10 to the minus 3 seconds, quarks combine to form the first hadron. So there is a lot of pair production taking place at that point. And still the temperatures are quite high. After 1 second, the creation of matter stops, and this is happening at 10 to the 9 Kelvin. At about 100 seconds, protons and neutrons fuse, so you'll have about 25% of the universe as helium, but not many heavier elements are created at that point, because the expansion of the universe is so quick. After 380,000 years, the universe starts cooling down enough to allow nuclei to capture electrons, so you have the first atoms forming at that point. Now, after about 30 million years, the first stars start appearing, where you have heavier elements forming. Then after 200 million years from the Big Bang, the Milky Way starts forming due to the gravitational forces that we've seen before in the previous chapter. Then after 9 billion years, the solar system forms from the leftover of a supernova, and then 13.7 billion years from the beginning. So now we have about humans evolving, so like about 200,000 years ago humans started evolving, and we have physics starting, and the temperature is 2.7 Kelvin only. Okay, so we have dark energy. Now, what is dark energy? We don't quite know exactly what it is, but it's been hypothesized that it exists because light from when they were studying light from distant supernova, they noticed that it was less intense than they predicted. So this led to a conclusion that the universe expansion was accelerating. But for it to accelerate, it needs a source of energy, which we can never detect. So they call that energy that we can't detect dark energy, which is a hypothetical form of energy that permeates all space. So we assume that around 68% of our universe is dark energy. So dark energy basically was formed to explain the accelerating expansion of the universe. So astronomers spend a lot of time investigating star velocities in different galaxies, and they expected that if this is let me just draw it quickly. If this is a galaxy, that the stars further out from the center of the galaxy will have lower speeds compared to the ones closer to the center. However, what they saw instead, they saw that it stays quite similar, the speed. Now, every single matter that we can see ourselves is near the center of the galaxy. So that means that if they are not slowing down, there must be another type of matter that we can't see. And they call that the dark matter. So the universe actually contains 27% of that matter. So we talked about 68% of dark energy, 27% of dark matter. This leaves only 5% of matter that we can see. So we only can see 5% of what makes up the universe. So there's actually not much that we also know about dark matter, as it we cannot see directly. It doesn't emit or absorb any light. So there's a lot of theories around it, but the idea is that dark energy and dark matter are something that need to be solved, and we have not much knowledge about it currently. So we have looked at the evolution of the universe after the Big Bang to the present time. So you just need to know the order of things that happen and kind of around the time that they've happened. And we looked at how the universe can be made of dark energy and dark matter, the reason behind them, why we are assuming dark energy and dark matter. So remember, dark energy is because the universe is expanding at an accelerating rate, whereas dark matter was hypothesized because of the fact that the speeds do not match in term of the stars do not match the position that they're in a galaxy that were calculated. So the predicted and observed speeds were different. So they said, well, if we can only see matter in the center, and we would expected the speeds at the edge of the galaxy to be moving slower, that means that there's mass that we can't see, and that's what they call dark matter. And we only know about the ordinary matter that we can see, which only makes 5% of the universe. So it's a good thing to know roughly the percentages of dark matter, dark energy, and ordinary matter.